In this video, I want to take a look at the dot product and matrix multiplication and see how each can be written in terms of the other. So let's start with the dot product as matrix multiplication. Now, when we think about the algebraic interpretation of a vector, it's a list of numbers. And we choose to write that list of numbers with pointy brackets and commas in between the numbers. And I have mentioned already that some books will use round brackets. However, you know, it's a list of numbers. Who cares what the notation really is, right? Whether you write it with pointy brackets or with rounded brackets or with square brackets and no commas, right? Or as a vertical list of numbers, or maybe as a diagonal list of numbers. It's still a list of numbers. And as long as you write them with a particular order in mind, then it is that vector that you're thinking of, right? It's that list of numbers. However, written in either this form here or that form here, it really looks like a row matrix or a column matrix, which really is why when you look at the notation that the book uses, they use the same notation that for column matrices and for vectors, right? That all the stuff we did in chapter 1, ax equals b, x was always written as a boldface x because it was just a column matrix. Well, now in chapter 3, X is going to be written as a column matrix, but we're going to think of it as a vector because it's a list of numbers. It's an ordered list of numbers. So what is the vector, right? Is it this or is it that? The answer is yes. It's whatever you need it to be. It's a list of numbers. The thing is, as a matrix, we can do matrix arithmetic with it and see that it's the same thing as the dot product that we're doing. So for instance, I'm going to think of two vectors here as row matrices. I'm choosing them in R3 just as a for instance, but you can do this in any Rn. So I've got U being U1, U2, U3 written as a single row matrix, and V1, V2, V3 also written as a row matrix. I want to look at the dot product, and my claim is the dot product is equal to the first vector times, the first matrix times the transpose of the second matrix. Right? So when you transpose that V1, V2, V3, you get this. Now I've got a 3 by 1 matrix. No, I don't. I have a 1 by 3 matrix times a 3 by 1 matrix. The result is 1 by 1. Now, it's a 1 by 1 matrix. It's a matrix with one thing in it. You can just think of what is the value in it, right? And when you look at what the value is, you're going to have U1 times V1 and U2 times V2 and U3 times V3 and add them up. That matrix multiplication there actually does that dot product. So thinking of these as row matrices, then the dot product is just one of them times the transpose of the other. Right? Likewise, if we think of them as column matrices, so U1, U2, U3 written as a column, V1, V2, V3 written as a column, then I claim that the dot product can be written as take the transpose of the first one times the second. Notice that when you take the transpose of the first one times the second, it looks just like it did up here, and of course you're going to get that same result, U1, U2, U3. Sorry, U1, V1 plus U2, V2 plus U3, V3. So there is the dot product written as matrix multiplication. Now I want to write matrix multiplication like it's dot product. So suppose I've got an M by R matrix, so M rows and R columns, A, and I'm going to write A this way, where R1, R2 up to Rm are the row matrices, the individual row vectors, I'm going to call them, right? The first row is a list of numbers. The second row is a list of numbers. So they're each vectors in R. Is that right? Each row has R things in it because there's R columns in this matrix. Likewise, if B is an R by N matrix, then I'm going to write B as a bunch of columns. So C1 is the first column, C2 is the second column, C whatever up to Cn is the nth column. And I call them vectors here. They're just R by 1 matrices, right? There's R rows and 1 column in each one of those columns. Now, when I multiply A times B, when you think about how we multiply matrices together, you take the first row of A and the first column of B, and you multiply them together and add the results. And then you take the second row of A and the first row of B, and you first row of A, sorry. Anyway, rows of A, columns of B, multiply them together, add the individual entries. Well, that multiplying and adding is exactly dot products. So when I have all these rows times all these columns, I take the first row times the first column. It's actually a dot product. And the second row times the first column. That's what's here. All the way down would be down to the rth row, first column. Then you move to the second column, do it times each of those. And by times, I mean dot product with each of those. Row of the first matrix, excuse me, dotted with a column of the next matrix. And so there we have, I think, a cleaner way of saying what's going on with matrix multiplication. You are, each entry, the entry in the ith row, jth column, is the ith row vector of A dotted with the jth column vector of B. Right? And in that way, you get an M by N matrix as a result.